Hi everyone, welcome to my channel. I hope you guys are doing great. And today it's my second video on tensor calculus for beginners. So for those who have not watched it yet, you have a link up in the above somewhere here, I guess, and in the description below. Today's topic is linear operators and matrices. So let's jump straight into it. So we start off by talking first about linear maps. And so linear maps or mappings. And so we start off by defining what that means. So let V and W be two vector spaces, meaning that they both satisfy vector spaces axioms. Then a mapping, let's say F, is linear if and only if, so we have a map F from V to W. For example, it takes a vector V and it maps it into F of V. Oops, so I'll basically say F of V, and that would be W, for example, in this space, and this is an element of W. So such that, what are the properties of linearity? It means that if F eats A, like let's say not A, let's say lambda V plus gamma U, it should split up F of V plus gamma F of U. Now remember, here there is a ambiguity in the addition and multiplication. As you know, we told that last time, and if you haven't watched it, you can watch it over here or in the description below, is that here this guy is nothing but lambda circle dot V plus gamma with a circle plus dot U. And here what happens is we have, so here you can say that this guy is in V like this to indicate, and here the circle dot is in W, so it lives in a different vector space. So, and this plus lives in the W space, so it's defined over W plus gamma circle dot W F of U, but we simplify it to this form. Why? Because we say that V is equipped with this addition binary operation and this scalar multiplication, and W is quite similarly equipped with an addition operation, which is in W, and then a dot operation, which is in W as well. But for the simplicity of notation, we assume that these additions are living in different spaces, but for which we have this kind of simplification. And here lambda, gamma, they are just elements of some field, algebraic field, and U and V are elements of the vector space V, such that this entire thing is an element of W. Now, the interesting thing about linear operators is basically that anything that satisfies this is a linear operator, and so we're going to denote them with this special thing. Instead of defining this in this way, we would define it like this: V to W, but I will make a tilt above the arrow, and that would mean that V would be mapped to V, F of V, in a linear fashion. So this is going to be a linear. This is going to be a linear map. Okay? And this is basically the point in linear maps. Anything can be a linear map if it satisfies this condition. If it does, then it's called linear maps. And why do we use them? It's because matrices are based on some sort of linear mapping, and especially we sometimes not denote them like this, so notational purpose. For example, in quantum mechanics, this is what happens. Linear maps are called linear operators, and it's a class of linear maps. And what you can think, how you can think of them is that instead of writing it f of v, we basically just write fv like this, or in my notation, so for linear operators, say, so linear operators are like matrices, they are kind of matrices, but they are linear maps, and what happens is that f, this is a linear operator, would eat a vector to spit out another vector, and we usually write this like this, fv, and so this means f, the operator, acting on v, the vector, and this is an element of w if v is an element of v, and that f would eat alpha v plus beta u and spit f hat v plus beta f hat u, and so it's still meaning that it's a linear mapping. Now, another interesting thing about linear operators is their representation. So representation of linear operators is this kind of interesting thing, because what do I mean by representation is meaning that you have to have a basis in your vector space. So let's say that we can decompose this vector v as the sum over I, vi, ei. Now, notation or convention, and this is called the Einstein summation convention, and we're going to use it a lot in tensors. So it's all over tensor. Without this, it's going to look like a mess in tensor calculus. And it basically says that if you have two repeated indices, then you sum them. So, and the idea is that you can basically just assume there is a summation already here present. And so it's like if there is a summation there. So whenever you see two repeated indices, it means a summation is implied. And so we can basically remove the summation sign just for simplicity of the equations, because then it gets really, really complicated. And the point in doing this, so we get v equals vi ei. And if an operator, a linear operator, acts on v, then it's going to act on vi ei. So here vi is an element of some field, maybe complex or real. Let's consider just a random field. And for the purpose of tensor calculus, we would use real, basically. And what happens here is that because this is a number, the operator won't act on it. So you can basically pull it outside. It's exactly this linearity property. And then we have f on ei, the basis. So it acts on the basis. Now, what does that mean? That means that we should have a new basis, because what happens here, we have a vi, and this is supposed to represent a new vector living in w. So let us call fv u, so we can call it u. And what happens here is that u is equal to vi times f hat on ei. But in order to do this, this must be some new basis. And you can call it whatever you like, and it's going, let's call it vi fi. This is a new basis. So ei is the basis in v, and fi, the set of vectors spanning the vector space w, is going to be a basis for w, the w vector space. And what happens here is that we said u is vi fi, and that means one thing. That means that this new thing, f acting on ei, giving you fi, it basically transforms bases in one vector space into others in the other vector space. And how does it do it? Well, it's as if we had something like this. So you can think of this f, or let's think of this small fi. This is where the representation of linear operators comes in. And it basically says that fi is going to be f, let's see what we can do here. Ij, ej. You can think of it like this. And so what you can say about this object is that it basically, you contract with j. So you have a summation over j, if you like. And you act your fi as the remaining indices to match up. And hence, you have fi equals to fij ej. And this is the representation version of this. So in a sense, fij ej is f hat ei, if you like. And so it's called the representation. This is called, so this fij is the representation of f under the basis ei's. And that means that these are what we call matrices. So matrices, you can call them matrices. And the point about matrices is, notice that I'm not using this notation. I'm using this one because I want to be able to directly apply this in the next video to tensors. And because this is what we call a 1-1 tensor. And a matrix is a 1-1 tensor. So what will happen here for this representation, or basically linear operators are 1-1 tensors. And here what we can call, so we can start talking about matrices from this point. And matrices are basically big, so this is the notation, you put brackets. Actually you can just do the following. You can just say f like this and ij, and that would mean that you would have number of rows and number of columns, and the number of rows is I, so you have f11, f12, and here you would have f21, f31, here you would have f31. And so what's happening, going to happen is that, if you go all the way down, you will have fmn. So if you have n of them, and here you have fm of them, then what's going to happen is that you will have fmn. So basically this is going to be m cross n times matrix. And that would mean that you have m rows and n columns. A very quick example, like discussed last time, is vectors. Vectors are column, so v1, v2 up to vm. So this is called a column vector. And you can also have row vectors like this. So these are v1, v2, vn, and so these are called row vectors, and they live in different spaces. So these two are different. They're different objects, actually, when we will talk about soon. So vectors are column vectors, and these are what we call either dual vectors, so they have their own name, or covectors, or even one forms. Depends on how you define them. So another nice example is the matrix, the square matrix. That means that m equals n. The number of rows and the number of columns are the same. So you would basically get a tensor sorry, a matrix with, let's say we have m equals 3. And so in this case, what you would have here, for example, let's call the matrix M, M11, M12, M13, M21, M22, M23, M31, M32, and M33 as your matrix. And this is going to be your 3 by 3 square matrix. These are called the diagonal elements, and these are basically the off diagonal. And it's sometimes important because there is something called the transposition, and transposition is basically this operation of taking a matrix, let's call it M, I, J, and transposing it, which means you would have to have M, J, I. And so it's typically like reversing the order of the rows and columns. So you reverse rows and columns. And by doing that, what you will have, for example, let's consider our matrix. Let's consider the matrix 1, 2, 3, 2, 3, 2, 1, 1, 3, say. Okay. If you have such a matrix, this transposition is this operation called T. And what will do this is that you keep the middle, meaning the diagonals. So you have 1, 1, 1, 1, 1, 1, but you reverse each of these. So what will happen? These two would change, these two would change, and these two would change. So you will get 2, 2, you get 3, 3, but here you will get 3, 2. And so this is the matrix, transposed matrix. You also have the zero matrix. And the zero matrix is basically just zeros everywhere. It's just 0 everywhere. And it's usually denoted like O with double bars or whatever you like. And the identity is this one, which is 1 everywhere in the diagonals and 0 everywhere else. And it is a square as well. It's a square matrix, and this is called the identity. And it usually denoted as, in my notation like this, with an I, with the number of rows and columns indicated. So for example, if you have an identity matrix for a 3 by 3 matrix, then you have 3 by 3, 4 by 4, 1 by 1. And for example, in space-time, we have this special matrix called the Minkowski matrix. And that one is -1. It depends. It's -1, 1, 1, 1, 0 elsewhere. You have the other one, which is 1, -1, -1, -1, 0. And you have these two conventions. And in old literature, you would have 1, 1, 1, -1. And it's like an identity, but it's not. So just pay attention. Now we have to talk about different types of matrices. So we have what's called Hermitian matrices. These are complex matrices, meaning that their elements here are all complex numbers. But this is key. When we write Tij, this is an element of some field. Because we said that, let's say Tij, Ej, that would be an Fi, then for this to hold, we have to have that these are numbers. Tij's are numbers, all of them. And that's why we can represent them as this whole tabular matrix. And the point about that is that if it's C, then a Hermitian matrix is going to be that the type of matrix is that T dagger equals T. So what that dagger means, dagger is basically complex conjugation with a transpose. So for example, not an example, but the property is that T dagger is T bar, which means complex conjugation, transpose, or T transpose complex conjugated. And if that is equal to T itself, then it's called T is Hermitian. Now another property is that because this is the symmetric matrices, and symmetric matrices are the matrices for which Tij, so the components of the matrix, are real numbers, and T transpose equals to T, then it's called a symmetric tensor. You have the antisymmetric tensor, antisymmetric matrices, sorry, not tensors, I'm way ahead, matrices, and they are the fact that T transpose equals to minus T. So if you like, in a representation notation, the following is the notation that we use is the following. So if you have Tij and transpose this guy, that means you have Tji, and that is equal to, if that is equal to minus Tij, then T is antisymmetric. If Tji equals Tij, T is symmetric. And if Tji bar equals Tij, then T is Hermitian. And Tji bar equals the minus Tij, then T is anti-Hermitian. So with these four matrices, you can basically form every possible representations you can make out of vector spaces. Güzel. Now the question of how the bases change, we know that. Now we have the question of how the components of vectors changes under a representation. And the answer is fairly simple, because we can write Fi as T, let's say F again, this operator Fij, Ej, but we also know that U was Vi, Fi. So I can rewrite everything Fij, Ej, and here you have this object, which you can call it Uj, Ej. So you have a summation over I, and then you bring the j. And so what happens here is that you have now Uj equals Fij Vi. So we have these two. We have these two equations. One representation helps transform bases from one vector space to another, and this one helps us to get from the components, the representation of vectors from one space to another. And so you can use both of them And usually physicists use this representation the most because that's what's happening. The thing that happens in tensors is that these are changing, even themselves would transform. And how do they transform depends on how you choose your components or your representation. For example, for general relativity, that we will discuss way later on in some other series of videos that would base on these tensor calculus videos, is that these Fij's would transform differently for different vectors. For example, this would be dx over dy, say. And so we would have dyi here, and this one would have an alpha. And then here we will have a dyj dx beta f alpha beta. And so you can see that this is how they transform themselves. So everything transforms. So here you can say uj would transform as some matrix, say dx, you can choose them, some dxj dx dy alpha u alpha, and the representations given a coordinate system, so these x and y are different coordinate representations. And so under different representations, you would have different transformation laws. These are transformation laws. So, and they must be linear. So linearity is required for both of them to hold, is that they must be linearly transformed from one space to another space, from one representation to another. And this is what we're going to use as the key definition for how we define tensors and all the other various types of objects. And so I'm keeping the dual vector spaces for next time, because that's going to be something that is highly related with linear operators and how they act. Because linear operators, they form a space by themselves. So the space of linear operators, and it's called dual. It's sometimes called dual, but it's called the space of linear operators, and it's usually denoted with different notations, either by L of, we have a vector space VW, so this is basically the set of all maps F such that it eats F, basically eats all F, that eats V and then splits linearly into W, or this thing called homomorphism of V to W, same notation. So you use either this one or this one. And for dual spaces, as we will see, dual vector space, if you choose W to be a field, then you get the dual vector space, the set of all dual vectors living in dual vector. We will discuss that in another episode. So this would conclude this video, and I hope you guys are enjoyed this, and I'll see you in the next video where I will talk about dual vector spaces and tensors. So we will now start talking about tensors. So stay tuned.